Good afternoon. Welcome back to Codex. Today we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Shuxing Li, who is a PIMS postdoc at Simon Fraser University. Shuxing is interested in design theory, coding theory, finite geometry, discrete geometry, and their interactions. Today he will tell us about packings of partial difference sets. Take it away, Shuxing.
Thank you, John, for the very kind introduction. This is a joint work with Jonathan Jedwab from Simon Fraser University, and my research is supported by the Pacific Institute for the Mathematical Science. Here is the outline of my talk. We're going to talk about partial difference set. First of all, I want to convince you that partial difference sets are underlying configurations that explain many two-valued phenomena in various mathematical branches. That's why we are interested in it. Secondly, I shall briefly introduce a character approach to analyze partial difference set. Then we move on to the main theme of this talk, the construction of Latin square type PDS. So PDS is short for partial difference set. Latin square type PDS is the most well-studied subfamily of PDS. Still, there are a lot of questions regarding its constructions. And we shall look at its construction via a fresh angle that is called LP packings. It is a configuration consisting of disjoint partial difference set in one group. Via this very proper angle, we can make progress on the construction aspect. We are able to unify many previous constructions as well as generate new ones. So I will give you the definition and some examples of LP packing, and particularly illustrate a very powerful lifting construction of LP packings. That is our plan today. So let's start with the motivation. I want to convince you that partial difference sets have strong explanatory power towards many two-valued phenomena. Let's see one simple example. We have a very simple graph, the 5 cycle. It is a strongly regular graph in the sense that for any two incident vertices, they share exactly 0 common neighbor. Whereas for any two non-incident vertices, they share exactly 1 common neighbor. So right here, we're looking at a two-valued phenomenon in terms of number of common neighbors. And actually, we can reinterpret this phenomenon using a different language. Let's take a finite abelian group G. In this case, G is the cyclic group of order 5. We have 5 group elements. Oh, there's something in chat. Okay, it's about mailing list. If you have, we have 5 elements in the group, and we use the 5 elements to label the 5 vertices. And we take a subset D of the group G containing 1 and 4. Now we impose a rule. 2 vertices A and B are incident if and only if the 2 differences generated from them form a subset of D. So applying this, this rule, for example, if we take 0 and 1, 0 differences are 1 and 4 form a subset of D. So 0 and 1 are incident. In contrast, consider 0 and 2. The differences are 2 and 3, not a subset of D. So 0 and 2 are not incident. Applying this rule, we can exactly recover our 5 cycle. And you may be wondering, what is the counterpart of the two-value phenomenon we have seen here? Well, we consider the translations of D, which is written as D plus G. So we always consider the non-trivial translation in which the element G is not the 0 element in the group. And by simple verification, we can see that take any translation and intersect with D, the size of the intersection take exactly two values, 0 or 1. And the choice of values depends only on whether the translation element G is in D or not. So I claim this two-valued phenomenon is the counterpart of the two-valued phenomenon of the common neighbors. How can we see it? Well, take a vertex H. We know that all its neighbors are D plus H, this set of translation. That is because for any vertex, if it is incident with H, then this vertex minus H must belong to D. Following the same idea, the neighbors of G plus H is just the translation D plus G plus H. And if we want to compute the common number of common neighbors between H and G plus H, we just do this straightforward intersection. And this intersection reduce to the intersection we have seen before. And it takes exactly two values. When G belongs to D, H and G plus H are two incident vertices, and they share exactly 0 common neighbor. When G is not in D, H and G plus H are non-incident, and they share exactly 1 common neighbor. So that's how we can interpret the two-value phenomenon in the language of a group and subset. So I think many of you are interested in the frame theory. And here is a very elegant example. We consider a matrix of size 3 by 16 consisting of plus or minus 1 entries. This matrix satisfies the following two nice properties. First of all, any two distinct rows are orthogonal. Any two rows has dot product equals 0. That guarantees this matrix, this frame is tight. Secondly, any two distinct columns have dot product either 3 or minus 1. So right here, we have another two-value phenomenon in terms of dot product. Because we are seeing two distinct values, this guarantees the frame has two distances. So, and I guarantee you that this example of two distance tight frame can be rephrased in terms of group and subset. Actually, we can choose some very proper group G and subset D so that G itself has the two intersection size property. And this property guarantees the two distinct dot products. So I will give you more details about this example in the next section. Up to this point, let me formally define our central object partial difference set. We take G as a finite abelian group of order V. So in this talk, when we mention group, we always mean finite abelian group. And D is a K subset of G. And for each non-identity element G in a group, the translation intersect D itself takes exactly two sizes, and the choice of sizes depends on whether G is in D or not. If that is the case, we call D is the VK lambda mu partial difference set, or in short, PDS in the group G. So there are 4 parameters for PDS. The first one, V, is the order of the finite abelian group G. Second, K is the size of the subset D. Lambda and mu are the intersection sizes. You may be wondering why we call this object as partial difference set. How is it related to difference? Here is an alternative definition. We take any distinct pairs of elements from D and collect their differences in a multi-set. So it's a set contains elements as well as its occurrence. We know that if each element of D occurs exactly lambda times, and each non-identity element outside of D occurs exactly mu times, then we call D is a VK lambda mu partial different set in G. So in other words, partial different set is an object whose differences has some very strong uniformity in terms of its frequency or occurrence. So as a technical assumption, we always assume the identity element is not in the subset D. If we take a subgroup H of G, then H minus identity is trivially a PDS of G. So we always interested in non-trivial PDS. So having defined the partial different set, hopefully I have convinced you partial different set are underlying objects explaining many two-value phenomena. Like we have seen before in graph theory, the 5 cycle, the strongly regular graph. Also in a frame theory about the 2-distance tight frame. And as a matter of fact, in many other mathematical branches. So that's why we are super interested in partial different sets. Okay, so having established the motivation, let me introduce a character approach to analyze PDS. Given a group G, recall its exponent is the smallest possible integer such that for every element in the group, G to the nth power equals the identity. That's the standard definition of exponent. And we shall see exponent is the crucial factor when we do the character analysis. So let's take G to be a concrete group 2 cross 5. And we immediately know its exponent is 10. Now we take an element in the group G. Each element would induce a character chi sub AB. And a character simply maps a group element to a 10th root of unity. We're using 10th of root of unity right here because the exponent of the group is equal to 10. In fact, every character induces a group homomorphism from the group G to the multiplicative group consisting of complex root of unity. And at this point, you may imagine character is actually a very efficient compressor. It distills the information of G into a well-understood cyclic group. And this cyclic group has order exponent of G, which could be much, much smaller than the order of G. So chi maps objects in G into a bunch of complex numbers. And there's one very particular character called principal character that is induced by the identity element of G. This principal character is somewhat boring because it maps all the group element to the number 1. So mostly we are interested in all the other characters which are non-principal. Non-principal would tell us more about a subset in the group G. As a side remark, we note that if we collect all the characters defined on the group G, we would form another group called character group denoted by G hat. And this G hat is isomorphic to group G. So why character matters? Here is a classical result. Essentially, this result dates back to Fourier because we are effectively doing discrete Fourier analysis. And Turing in 1965 set this result into the modern language and made it well known to the different set people. So the result is saying, given a group G and take a subset in it, we notice the group G has exponent n. Now take any character, apply it to the subset D. This chi of D is nothing but apply chi to every single element in the subset D and then take the summation. So chi of D is just a summation of nth root of unity. And the key point is if we apply all the characters chi to D and get a sequence of character values, this sequence of complex numbers retain full information of the subset D. So knowing one hand, you know the other hand for free. This is the crucial point in which we can use a character theory to analyze the subset D. Okay, with that, let's go to the scenario of partial difference set in which the characters behave even nicer. So let's take a group G, which is 3 by 3. We have a subset D of size 4, which form a 9, 4, 1, 2 partial difference set in group G. And if we apply all the non-principal characters to D, we see exactly two integer values, either -1 or 2. So right here, we are looking at a two-value phenomenon in a character length. And very nicely, those two values are actually integers. So we are ready to introduce our major object named Latin square type PDS. Simply looking at this name, you may wondering this kind of PDS has something to do with the combinatorial configuration called Latin square. However, the relation between Latin square type PDS and Latin square is very much indirect. So I won't introduce the connection right here. It is a very, in hindsight, it is not very good name, but the mathematician has made so many such names. Okay. One thing about Latin square type PDS is that, remember, for PDS, we need 4 parameters to decide we need 4 numbers to decide its parameters. However, for Latin square type, we need only 2. If we specify 2 numbers n and r, then the 4 parameters follows from those n and r. So knowing n, we know the order of the group must be a square, n square, and knowing n and r, we can derive the last 3 parameters. So looking at Latin square type PDS from the character angle, we have the following very elegant, necessary, and sufficient condition. D is an NR Latin square PDS if and only if D has the right size. And if we apply non-principal characters to D, we see exactly 2 integer values. That's the very elegant characterization of Latin square type PDS. In fact, if you look back to our example, this is exactly a 3-2 Latin square type PDS. So now this is the right timing to revisit our 2 distant tight frame example. I want to convince you this tight frame is connected to a Latin square type PDS. So we take the group G equals to Z2 to the 4, the elementary abelian 2 groups, which has exponent 2. We take a subset in the group G. This subset is a 4-1 Latin square type PDS in G. And using the subset, we can form this 2 distant tight frame in the following way. We label the 3 rows using the 3 subset elements. We label the 16 columns using the 16 vectors defined on G. And the entry inside the matrix is just the corresponding character applied to corresponding group element. So for example, in this column, I can easily read off chi G of D1 is -1, chi G of D2 is +1, chi G of D3 is -1. Because G has exponent 2, we shall always see plus or -1 across this matrix. And because D is a Latin square type PDS, we know its character value is either 3 or -1. That guarantees the dot product of distinct columns is either 3 or -1. So we have a 2-valued phenomenon in the character length explained the 2-valued phenomenon in dot products. So let's conclude our example. And now let's move on to the main theme, the construction of Latin square type PDS. So the first thing to mention is for the construction of Latin square PDS, the structure of groups matters a lot. For example, we know that there are two groups of order 9, 3 by 3 or cyclic 9. And in 3 by 3, we have thin example of 3-2 Latin square PDS in G. And if we apply non-principal character to D, we should get a summation of 4 third roots of unity. And this summation should always end up with -2 or 1. That is our example in 3 by 3. In contrast, in the cyclic 9, the situation is completely different. There's no non-trivial PDS in cyclic group 9. And we have a very intuitive explanation from the character viewpoint. So we just take a D to be an arbitrary K subset of G. And we apply a non-principal character to D. So chi of D is a summation of K ninth roots of unity. So because the exponent of G is 9, now we have to add up 9th roots of unity. And in contrast to third roots of unity before, it is more unlikely to add up 9th roots of unity and get integers. That's why in cyclic 9, we can't have non-trivial PDS. So those two examples are showing us in group with low exponent, it's easier to construct PDS, whereas in group of high exponent, the construction becomes increasingly difficult. And in some extremal case, there's simply no PDS in high exponent group. With that, let's look at the character viewpoint a little bit more to give you a bit more taste on this approach. So once again, we have the example of Latin square type PDS in 3 by 3. And if we arrange the 9 character values in a 3 by 3 array, we have something like this. So the top left corner is associated with the principal character. So this number is telling us the size of the subset D. All the other entries corresponding to non-principal characters, and as we have seen, those values should be either -2 or 1. Okay, now we modify the subset D a little bit. We replace the element 0, 1 by 1, 1. And again, consider its character values. Now on the right-hand side, we see a much worse character table with complex numbers involved. So this phenomenon is telling us there's no easy way to approximate a partial difference set because a very small discrepancy would result in completely different character table. Also, if you just choose a subset randomly, and you will almost always end up with a character table on the right-hand side, a very massive one involving complex numbers. So random approach does not work very well for partial difference sets. So we have to have some insight to construct partial difference set. So let me showcase our contribution using a group of specific order 3 to 10. It is well known that in the cyclic 3 to 10, there's no non-trivial PDS, whereas in the elementary abelian 3 to 10, there does exist Latin square type PDS. So we can draw an interval, put those two cases on two extremos. On the left-hand side, we have the highest exponent, and right-hand side, lowest exponent. And there's a big question mark lying in between. We're asking what happens to the groups in between. Do they contain Latin square type PDS? Well, Up to isomorphism, there are in total 41 abelian group of order 3 to 10. Among them, 8 of them are known to contain Latin square type PDS. Those are the 8 groups. And it is easy to list those groups, but actually they are consequence of a series of research. The brief story is up to 1990, people understand the Latin square PDS in elementary abelian groups really well. And after that, over the course of more than 30 years, many different authors tried to construct Latin square type PDS in non-elementary abelian groups. There have been many completely different constructions, and there are mainly 3 approaches. The first approach is to use ring theory. Given a ring, we not only have the additive operation, but also the multiplicative operation. So people used the multiplicative structure very well to construct partial difference set. The second approach is the number theory approach, which involves very delicate character sum computation. And the third one is applying some highly nonlinear function. So for some very structured function, its image set naturally give us some BDS. So those 3 approaches are very different from each other, and it would be really surprising that they share some common structure so that you can propose a common framework to unify all these constructions. And in fact, that is exactly what we have done. We did propose a unified and elementary approach to replicate all these previous constructions. And more to the point, we are able to construct Latin square type PDS with new parameters. To achieve this goal, we need some insight. And this crucial insight is to look at Latin square type PDS from the very right angle. Instead of considering one single Latin square PDS, we should study a much stronger configuration named LP packing. It is a collection of disjoint Latin square PDS with nice mutual property. So we consider a much stronger object, and this LP packing is a packing of partial difference set, which reflects the title of this talk. And once we have the conception of LP packing, it is an easy exercise to construct Latin square PDS from it. Okay, so next I shall move on to LP packings and give you some examples about it. So let's start with LP packings in elementary abelian group, and they can be obtained from the object called spread. So take group G to be that 3 to the 4. This group contains exactly 10 subgroups HI. Each of them has order 9, and every 2 of them intersect trivially. So those 10 subgroups form a spread in our group. And we can modify our spread to get our LP packing. Take the spread. For the last 9 elements, we throw away the identity. This gives us a collection of 9 members. Those 9 members form a LP packing in group G relative to the first group H0 we haven't used. And we would like to look at LP packing via the angle of characters. Each HI minus identity is a Latin square type PDS. If we apply character to it, we shall always get -1 and 8, exactly 2 integral values. More to the point, if we take the same character and apply it to the 9 members simultaneously, we would get a multi-set of 9 values. And those 9 values has exactly 2 choices. either always -1, or one of them is 8 and all the others are -1. And the choice of those two sets depends only on whether chi is principal on H0 or not. Chi principal on H0 means chi sends every element in the subgroup H0 where relative 2 to the number 1. So to some extent, we have extend the two-valued phenomenon from each individual PDS to a collection of PDS. And let me reiterate the LP packing using a diagram. We denote HI star to be the HI minus identity. Those 9 members is an LP packing in G relative to H0. So we use a table in which each column is documenting the character values of the members in the LP packing. So for each column, you see exactly 2 values, -1 or 8. And those members satisfy some nice mutual property. If you read across the table, whenever chi is principal on H0, you shall always see constant -1 value. Whereas if chi is non-principal on H0, you shall see exactly 1, 8, and all the others are -1. So given this nice property, we can derive that taking the union of members in LP packing, we will cover all the elements in G except those in the subgroup H0 that we are relative to. That's why we call H0 is the avoided subgroup. And if we have an LP packing ready, then we can take an arbitrary union of its members to get Latin square type PDS. So in one sentence, given a LP packing, we can construct multiple Latin square PDS. So to construct Latin square PDS, it suffices to construct LP packings. And here comes our major result. We are able to construct LP packings in even copies of cyclic group of prime power order. And the group we are relative to is U, which is an arbitrary group whose order is the square root of the ambient group. This theorem is powerful in the following sense. Remember, we have that constructing partial difference sets in group with high exponent is considered to be difficult. And right here, we can construct a much stronger configuration, an LP packing in groups with exponent p to the a. And a is an arbitrary positive number, a positive integer. So we actually construct LP packing in groups with arbitrarily high exponent. Secondly, we have a very good control on the avoided subgroup U. This group could be any subgroup with a proper order. So somehow this theorem offers us a very neat and clean viewpoint towards Latin square type PDS. And using a straightforward direct product construction, we are able to extend LP packing to direct products of groups of the same form. So this corollary recovers many previous construction using one single unified and also elementary approach. And I should reiterate, instead of constructing one single PDS, we are able to construct a collection of them. And more to the point, using LP packings, we can obtain Latin square type PDS with new parameters. And here is one of the example. So at this point, in the rest of this talk, I would like to give you a brief taste about a crucial construction, the lifting construction in our paper. So basically, in order to construct LP packing in high exponent group, we use a lifting approach. We started in elementary abelian group, and its LP packing is equivalent to the spread. And somehow we apply some lifting construction to get LP packing in higher exponent groups. So the lifting construction is the last part of my talk. So why the lifting construction is difficult? Let's recall that each member of an LP packing is a Latin square PDS. As the exponent of groups grows, the construction of PDS becomes really, really difficult. Also, the PDS in LP packing must be disjoint, and the union of them avoid a subgroup. Those are very, very strict restrictions on this collection of subset. So to manage the construction, we have to use some deep idea. The first one is a double lifting approach, which is proposed by Davis and Jedwab in 1997. Recently, they have refined this approach to work on all groups order to 258. So among the more than 50,000 groups of that order, they can conclude for every group, either it contains a different set or not. So this double lifting idea is the most powerful construction to my viewpoint. And secondly, to address the disjointness and the voided subgroup, we have to use an auxiliary configuration named LP partition. So I won't give you the definition of LP partition, but just use a diagram to illustrate our construction. So right here, we have two vertical lines. On the left-hand side, it's the lifting process of LP packings. On the right-hand side, it is the lifting process of LP partitions. So step one, we are able to construct LP packing and LP partition in elementary abelian groups. And we can do so by modifying our very nice spread in those groups. So step one, we set up the ground level. For step two, we go to the right-hand side. We proposed a lifting construction for the LP packings. It is a recursive one, starting from the level P, we go up to level P squared, level P cubed, and we can continue. So step two, we get a collection of LP partitions with arbitrarily high exponent. Now comes the very neat part. To finish the recursive construction, we want to combine the LP packing in the P level and the LP partition in P square level. By combining those two, we got a LP packing in the P squared level. Okay, so this LP packing serves as the seed for the next level. For the next level, we just use LP packing in P squared and LP partition in P cubed to construct LP packing in P squared. Okay, so indeed, it's a double lifting construction. And to give you a little more detail, we can imagine the LP packing is the core part of the construction, and LP partition is the shell part of the construction. To get an LP packing in P squared, we just combine the core, which is from the LP packing one level lower, and the shell, which is from the LP partition of the same level. And the key idea of the construction is to separate the LP packing into the core and the shell part. For those two distinctive parts, we have to apply different lifting rules. That's why this construction is somewhat delicate. And let me conclude by emphasizing lifting construction is a very powerful mechanism to simultaneously manipulate multiple subsets subject to strict restrictions. And here are some further research problem I believe is of significant interest. So remember, we always use our spread as our starter to do our lifting construction. And the spread only exists in elementary abelian group with even rank. So elementary abelian group, which is an even number of direct product. And we are asking, how about the odd rank group? How about group of such form? Can you find out some nice starter which plays the same role as LP packing so that we can apply our lifting procedure? Secondly, we are asking, is there any other situation to apply LP packings and the lifting constructions? So with all that, here is our major reference, and thank you so much.
All right, thanks so much. I'm going to hit that reaction button, and I encourage you to do so as well. And I think Dustin can hit the